My name is Xiaokuan Zhang. I'm from the Ohio State University. Today I'm going to present my paper, OS-level side channels without Procfs, exploring cross-app information leakage on iOS. This is a joint work with Xueqiang Wang and Professor Xiaofeng Wang from Indiana University, Xiaolong Bai from Tsinghua University, and my advisor, Professor Yingqian Zhang from the Ohio State University. So, side channel attacks are attacks that make use of seemingly harmless information to infer sensitive information. And mobile side channel attacks are side channel attacks on smartphones, which mainly have three categories. The first one is cache side channels, where the attacker and the victim share CPU caches. The second one is sensor-based side channels, where the attacker can learn the victim's information via sensor readings. Such sensors include GPS, accelerometers, gyroscopes, etc. The third one is OS-level side channels, where the attacker can infer sensitive information through publicly accessible interfaces and APIs. So in this paper, we focus on OS-level side channels. Let's first take a look at OS-level side channel attacks on Android. The typical threat model is that the malicious app controlled by the attacker is running in the background in the victim's device, calling the APIs to learn information about the user's activity. So Android system has a Procfs pseudo-file system that provides system information such as virtual physical memory usage, network traffic, CPU usage, etc. Most of Android side channel attacks utilize the Procfs by querying some per-app information files frequently to learn the user's activity. As a result, Android gradually removes information in Procfs to reduce the attack surfaces. Now let's switch to iOS. iOS does not have a Procfs, essentially shutting down the main avenue for the Android-style inference attacks. Also, since iOS 9, Apple has forbidden a sandbox app to access information about other running processes. As a result, it's impossible today to conduct a side channel analysis on iOS by exploiting per-app statistics, which completely defeats most demonstrated attacks on Android. Therefore, to our knowledge, there was no reported OS-level side channel attack on iOS. So, is it still possible to conduct OS-level side channel attacks on iOS? The short answer is yes, and I will show how this can be done in my presentation. Here's the outline of my presentation. I will first introduce threat model and attack vectors on iOS, then talk about three categories of attacks. After that, I will present the practical issues and countermeasures, then the conclusion. Now let's look at the threat model. Our threat model is that the attacker publishes a monitoring app in the App Store, and the user downloads it onto his phone. This app is disguised as an audio player. In other words, this app is similar to other music playing apps such as Spotify, Pandora, or iHeartRadio. Here are the new attack vectors in iOS we found. The first is host statistics 64. It shows the global usage of memory resources. The second one is get if adders. It shows the global network traffic. The third one is file exists at path method of NS file manager class. It can be used to test the existence of a file or directory. Later in my presentation, I will show how these APIs can leak side channel information. So now let's go to the first attack, classifying user activities. This figure shows the process of launching Amazon, Yelp, and Spotify consecutively on iOS. We call the APIs host statistics 64 and get if adders to get global virtual memory and network traffic time series, and we plot the diff series in this figure. This figure clearly shows that for different apps, there's a different pattern. Therefore, time series can leak information of user activities. In this case, the foreground app information is leaked. So, how can we combine the multiple time series to perform the inference attacks. This method should be able to first combine multiple time series, and second, reduce the dimension of the data. Previous work mainly deal with one-dimensional time series. So our method has three major components: ASIX, VOP, and libsvm. For the sake of time, please refer to the paper for technical details of our implementation. Now let's jump to the case studies. So for the experiment, we use a jailbroken iPhone 7 with iOS 10.1.1. Jailbroken phone is used only because we want to automate the process. It's not a requirement for our attack. Later in the practical issues, I will show the experiments on non-jailbroken phones. So our monitoring app is running in the background, and it collects the first 5 seconds data points after app launching by calling the API's IO rate of 1,000 times per second. The target app was terminated after each round. So our first case study is identifying program apps. We download 100 apps from top charts in App Store, and we choose another 20 pre-installed apps. We used top-end accuracy to evaluate our result. So this figure shows the result. We can see that for 5 seconds data, the top 1 accuracy is about 90%, and the top 3 accuracy is 97.5%. The same method can also be applied to inferring the websites that the user is visiting via Safari. We can achieve about 85% top 3 accuracy for 5 seconds data. So besides these two cases, we also have another example about Apple Maps in our paper. If you are interested, please refer to our paper. So now let's go to the second attack, detecting sensitive in-app activities. Some in-app activities may leak users' information. So first, let's look at an example of in-app activities. This is a blockchain wallet app after logging in. It's a finance app that performs transactions on Bitcoin instead of real money. So if we click the send button here, you will jump to the send page, asking the user asking the user to enter the receiver's address and the amount of Bitcoin to send. After that, by pressing continue, we go to the confirmation page. Once we click send, the Bitcoin will be sent to the receiver, and the transaction will be recorded, and is publicly available. Note that the Bitcoin address is anonymized, and it changes each time a user makes a payment. However, there is a record for each transaction. If we can identify the payment events and record timestamps, we can search the public records for correlation and further bind the Bitcoin addresses to the user. So the key here is to identify the payment event. For different UI, there will be a different virtual memory pattern. So to identify the payment event, we use an extended DTW method to do the pattern matching based on the VM traces. And the result is shown in the heat map. Our goal is to identify the payment event, which is index 0 in the heat map. And in this heat map, each row and column represents one activity, and cell ij represents average distance between activity I and j. So note that the distance are normalized in each row, so that the average distance between traces of the same activity is 1, and the distance from other activities are normalized accordingly. After normalization, the diagonal values are 1. So in this heat map, lighter color means longer distance. We can see that the distance between the payment event and others are quite large, so our method can easily identify the payment event. We also perform an empirical experiment by doing Bitcoin transactions by ourselves. The basic idea is that we collect a list of timestamps of transactions. Then for each timestamp, we can query the public Bitcoin transaction database to find a transaction set containing all transactions that happened around that time. After that, we can find the overlapping Bitcoin addresses, which are the ones that belong to this user. Here are some example transactions of our experiment. We can see that there are connections or common addresses between them. Therefore, we are able to link Bitcoin addresses to a certain device using this method. We also conduct similar experiments on Venmo and Twitter because they also have public database that we can correlate with. Please refer to the paper for details. Now let's look at our third attack, bypassing sandbox restrictions. So we measure the execution time of the file exists at pass API on a non-jailbroken iPhone 7 with iOS 10.2.1. We test using an existent and non-existent file path, which our app has no permission to access. Even though the API always returns false, we can see that there is a huge timing difference. Therefore, we can use this timing channel to reliably detect whether a file exists or not. Now let's look at our case studies to see how to utilize such a channel. So first, it can be used to detect whether an app has been installed on a device, which may reveal private information of the user. Here are some examples of sensitive apps. Divorce Force can reveal your marital status, and Asthma MD can reveal your health information. Pregnancy Plus may show that you or your close one is having a baby, and Sugar Sense may show that you have diabetes. So, why are we able to use the timing channel to detect the apps? The reason is that if this app requires permission for sending push notifications, or it dynamically registers home screen quick actions, a file with specific name will be created. As a result, by detecting the existence of such files, we can learn whether such apps are installed. We further studied top 150 apps in App Store's top charts as of August 2017, and push notification was requested by about 45% of the apps, and 31% of them have dynamically registered home screen quick actions. This side channel can also be used to detect number of photos and memos on the device, and there can be other case studies as well, since our method provides a generic way to detect the existence of files. So now let's look at some practical issues. First, App Store vetting. So our app is disguised as an audio player and successfully passed vetting. After our app was approved by Apple, we download the app and withdrew it immediately. Power consumption. So we measure the power consumption of our monitoring app on a jailbroken iPhone 7 with iOS 10.1.1. After 60 minutes, only 5% of battery was consumed. So to demonstrate the practicality of our attacks, we manually collect traces on a non-jailbroken iPhone 7 running iOS 10.2.1. Then we use previously collected data as training set or signature to evaluate the attacks. Note that the training traces were collected 20 days before the new test set on a different device with a different iOS version. So we randomly select 20 third-party apps and manually collect traces to construct the new test set. This figure shows the accuracy, so we can still achieve about 80.5% top 1 accuracy and 91.5% for top 3. So similarly, we also recollect traces of blockchain wallets and redid the evaluation. This time, x-axis means non-jailbroken device, and y-axis means jailbroken device. We normalize the distance per row as mentioned before. So this result is noisier than the previous one, but the payment activity, index 0, can still be clearly distinguished. So from these experiments, we show that our demonstrated attack are robust enough to be trained on a device owned by the attacker and then test using the data collected from the victim's device. Minor differences in the iOS versions and app versions can also be tolerated. So now let's see the countermeasures we proposed in the paper. So in our attacks, the monitoring app calls the APIs at a rate of 1,000 times per second. It's intuitive that rate limiting may be a good defense. Therefore, we filter the data and only keep every 1,000 over n's data point, and re-evaluate our foreground app classification. Here's the result. We can see that even if the rate is limited to 10 times per second, we can still achieve about 70% of one accuracy. When the rate reduced to 5 times per second, our method no longer works. So we report this result to Apple, and the rate limiting has been implemented in iOS 11.1 for host statistics 64. It's limited to twice per second. Another countermeasure is to mask the digits of return values. We can see that masking 3 digits can lower the accuracy drastically. So Apple has also implemented this approach for get-if adders to route the values to 1K bytes. The timing channel of file exist at path has also been eliminated in iOS 11. There are some other possible countermeasures, such as removing the APIs, runtime detection, and privacy preserving statistics reporting. So here comes the conclusion. So in this paper, we proposed the first exploration of OS level side channels in iOS. We showed 3 categories of side channel attacks. And these attacks showed that, similar to Android, cross-app side channel attacks on iOS are also feasible. So our study has helped Apple mitigate these security threats in iOS and macOS. So thanks for your attention. I'm ready to take questions now.
So I wonder, for to study and discover the side channel and the corresponding attack, what kind of execution, tracing, or instrumentation tool that you might have to use for tracking the execution of the apps and also the operating system? Because studying iOS is kind of renders some additional technical or engineering challenges.
So in our study, we didn't use any existing tools. So basically, we have a monitoring app which has a background permission, audio background mode, and it can run in the background, basically. So it's just like any music playing app. So when it's running in the background, we can call such APIs frequently to gather the information. And then we use some machine learning techniques to extract the signature of these foreground apps or the websites.
Is there any possibility that you might release that monitoring app?
Yeah, I'm not allowed to release it. So actually, I send my code to Apple.
Gotcha.
And I have had about 5 or 6 meetings with Apple's engineers.
Sure. Yep.
And to address these problems. So after about half a year, 6 months, they finally address it in iOS 11.
Yeah, this is great. Yeah, I congratulate you on the real-world impact that your work created.
Thanks.
Yeah. Any other questions for Xiaoquan? If not, let's thank Xiaoquan one more time.